This is Chapter 10, Section 5. We're dealing with changing equilibrium conditions and Le Chatelier's principle. So we've been talking about equilibrium reactions and equilibrium systems where the forward rate of reaction is equal to the reverse rate of reaction, and this leads to constant concentrations for all of the substances involved and apparently no change at a macroscopic level that we can observe. However, if you were to change the conditions of a reaction at equilibrium, this would disturb the rates of the forward and the reverse reactions such that they might no longer be in balance with one another. This can cause the reaction to be shifted towards one direction or another. It could be shifted to the right, in which case it would be producing more products, or it could be shifted back to the left, in which case it would be going back to make more reactants. Le Chatelier's principle tells us that when we disturb an equilibrium like this, when we apply a stress to an equilibrium, the system itself tends to respond by shifting in the direction that will relieve the stress that we just applied and restore the equilibrium. To help illustrate this, we can consider this analogy with two tanks partially filled with water and connected by a channel or a tube between them. Initially, the two tanks are at the same exact level because the tube connecting them allows the water to equilibrate between the two. Molecules of water still flow from the left to the right and from the right to the left, but the rates of flow in either direction are balanced so that there's no change in the amount of water or the water level in either tank. If we were to add additional water to one of the tanks, in this case into tank A, this would disturb this equilibrium. Tank A now has a bunch of extra water relative to tank B. This additional water is going to cause more of a flow from left to right than from right to left. So the right to left flow hasn't necessarily changed, but the left to right flow is now much larger because there's more water, there's more pressure pushing water to the right. So we've disturbed the equilibrium, and the system is responding by shifting to the right. Over time, it'll reach equilibrium again at a new equilibrium point. Some of the water from the left will flow into the right. As the water increases on the right-hand side, then the flow from the right to the left will also start to increase, and at some point they'll become equal again. At this point, this happens when the levels of water in both tanks are again equal, although they're equal at a new position relative to the original equilibrium. So the system has shifted to the right, but it's done so in order to establish a new equilibrium. Now keep in mind that this is only an analogy, and so in a real reaction you don't have equal amounts of reactants and products. You have amounts of reactants and product that are determined by the value of Kc, the equilibrium constant. This picture illustrates the same idea using actual molecules this time. So here we have an equilibrium reaction between hydrogen gas, these two white spheres joined together, and iodine gas, these two purple spheres joined together. And these react together to combine and form hydrogen iodide, where one white sphere joins with one purple sphere. You get two molecules of hydrogen iodide out of a reaction like this. Again, this is reversible, so this can go in the other direction. So we're starting with a system that is at equilibrium. In picture A, we already have an equilibrium system where there are 3 molecules of hydrogen, 3 molecules of iodine, and 1, 2, 3, 4, 5, 6 molecules of hydrogen iodide. This is the equilibrium mixture at the beginning. To this mixture, we're going to add 2 more molecules of hydrogen gas. This is going to disturb the equilibrium. So at the point where we've just first added those, we have now a disequilibrium. Instead of just the 3 hydrogen molecules we started with, 1, 2, 3, we now additionally have 2 more, for a total of 5 hydrogen molecules. We still have the 3 iodine molecules because we didn't add any more of those, and we still have the 1, 2, 3, 4, 5, 6 hydrogen iodide molecules because we didn't add any more of those. But these numbers are not in equilibrium between these components. So what's happened is that since we have now more hydrogen, there's going to be a higher probability for hydrogen to combine together with iodine to produce hydrogen iodide. So you can see here an example of a hydrogen molecule combining with an iodide molecule. And so when this is allowed to again reach equilibrium, we end up with 1, 2, 3, 4 molecules of hydrogen, 1, 2 molecules of iodine this time, and 1, 2, 3, 4, 5, 6, 7, 8 molecules of hydrogen iodide. So what's happened is that by adding more of the reactant molecule, hydrogen, we've ended up increasing the amount of product, hydrogen iodide. By increasing the amount of hydrogen here, we have shifted this reaction to the right-hand side so that it produces more hydrogen iodide. Now, in the process, the iodine has been consumed somewhat. Some of the initial iodine that was there was used up and reacted with the new hydrogen that we added to produce the product. But overall, the disturbance in the equilibrium was such that we shifted to the right and produced more product, more hydrogen iodide. So again, in terms of Le Chatelier's principle, we added hydrogen, we added a reactant, and the system, in order to resist that change, wanted to get rid of the reactant. The way that this system gets rid of reactants is by taking them and converting them into products in what we call the forward reaction. So we've seen what happens to this equilibrium when we add more hydrogen. This increases the rate of the forward reaction because we've increased the amount of hydrogen, and so this causes an imbalance towards the right-hand side, causes the equilibrium to shift towards the products. What happens if we were to add more hydrogen iodide at equilibrium? Well, in this case, Le Chatelier's principle would tell us that the system is going to shift to eliminate the hydrogen iodide that we've added, and this does that by shifting to the left. Hydrogen iodide would be consumed and turned back into hydrogen and iodine. So the reverse reaction rate would be increased, and the balance would shift towards the reactants. On the other hand, we could also get rid of some substances. Instead of increasing the amounts, we could decrease the amount. If we decrease the amount of hydrogen gas, this is going to decrease the rate of the forward reaction, which will make it smaller than the rate of the reverse reaction, which means the reverse reaction will win out. In terms of Le Chatelier's principle, we can say that by removing hydrogen, the system is going to look to replace that hydrogen or resist the removal of hydrogen by creating more hydrogen. And this reaction creates more hydrogen when it goes from right to left, when it shifts towards the reactants. Same thing if we were to remove hydrogen iodide, but in reverse. In this case, Le Chatelier's principle tells us that by getting rid of hydrogen iodide, the system will want to increase the production of hydrogen iodide by shifting to the right. And so by removing hydrogen iodide or removing any product, we're going to shift the reaction towards the product side. This chart summarizes those differences, but again, this is all encapsulated in the concept of Le Chatelier's principle. If you increase the amount of reactant, the system is going to want to try to get rid of reactants by shifting towards the products. If you decrease the amount of reactant, the system will try and replace the reactant that you eliminated by shifting back towards the reactants. If you increase the product, it'll shift towards the reactants to get rid of the product that you added. If you remove product, it'll shift toward the product to replace what you took away. Until now, we've just been dealing with changes in the concentrations of the reactants or the products, either by adding or removing substances physically to the reaction system. But there are other changes that you can make to an equilibrium system which will have a similar effect or cause a shift in the equilibrium. So for example, if we have a gas phase reaction and we change the volume of the container, it can shift the reaction in one direction or another. But it depends on the details of the reaction. It doesn't always shift in the same way for every reaction. So for example, whenever you decrease the volume of the container, the effect that that's going to have on the substances is going to be to increase their concentrations. It's going to be the same amount of matter in a smaller volume, which is a higher concentration. But this is true for all of the gases in the system or in the reaction. So it's not immediately clear whether it would shift to the left or the right because we're increasing the concentration of everything. However, Le Chatelier's principle tells us that if the disturbance of the system is to increase the concentrations, then the system is going to react in a way that decreases the concentrations to counteract that effect. the way that a gas phase reaction can decrease the concentration of the equilibrium system is by shifting towards whichever direction has fewer moles of gas particles. So in this case, you have 2 moles of gas particles of carbon monoxide plus 1 mole of gas particles of oxygen on the left-hand side. So that's a total of 3 moles of gas on the left-hand side. On the right-hand side, you have only 2 moles of carbon dioxide. And so for this particular equation, shifting to the right decreases the number of moles and therefore decreases the concentration. So for this particular equation, if you decrease the volume of the container, it'll shift the reaction to the right. On the other hand, increasing the volume of the container will decrease the concentrations of all the substances, and Le Chatelier's principle says that in order to counteract that decrease, the system will try and create more particles to fill in the empty space. And so, again, this particular equation produces more moles of gas by shifting towards the left to produce CO and O2, because there are, again, 3 moles on the left and only 2 moles on the right. This picture is going to illustrate the same point using this chamber, which has a volume that can be changed, and drawings of the actual molecules involved in this equilibrium. So initially we have this volume and the system is at equilibrium. Now at equilibrium here we have 1, 2, 3, 4 molecules of carbon monoxide. We have 1, 2 molecules of oxygen, O2, and we have 1, 2, 3, 4 molecules of CO2. If we decrease the volume of this system, this is going to compress the molecules together and increase the concentration of all of these substances. This is going to give us less space. The system is going to want to free up some space in response. It's going to try and counteract the change that we made. So if our change was to increase concentration, the system wants to get rid of some substances to decrease the concentration. Or if we think about it as decreasing the space between molecules, the system is going to want to get rid of some molecules in order to increase the space between them, to counteract our change. And so for this particular reaction, again, we have 3 moles of gas on the left-hand side and 2 moles of gas on the right-hand side. So in order to get rid of some molecules to free up some space, it's going to shift to the right. Decreasing the volume compresses the gas and increases the pressure. To relieve the pressure, the reaction shifts towards fewer particles. It shifts towards the right-hand side. And so what that means is that this new equilibrium, we have 1, 2 moles of CO, we have only 1 mole of O2, and we have 1, 2, 3, 4, 5, 6 moles of CO2. So in other words, we went from 10 molecules altogether to only 9 molecules now. So we used up one of those molecules, we decreased the number of molecules, and so we relieved the pressure and freed up some more space. On the other hand, if we were to increase the volume of this system, this would create a bunch of new space. This would decrease the concentration of all 3 components. And so now, in order to resist that change, the system would shift to the left-hand side in order to increase the number of particles and to regain some of the concentration that was decreased by expanding the volume. And so here we have 1, 2, 3, 4, 5, 6 molecules of CO. We have 1, 2, 3 molecules of O2, and we have 1, 2 molecules of CO2. And so here we actually have 11 molecules overall. Right? So we started with 10 molecules of gas. In this case, we went down to 9 molecules of gas, and in this case, we went to 11 molecules of gas. And again, this is based on changing volume conditions, changing space available in the system. For reactions that absorb or release heat, which is most of them, the equilibrium can also be disturbed by a change in temperature. So a temperature change should be looked at as the addition or subtraction of heat to the system. For example, in this endothermic reaction, we have nitrogen gas, N2, plus oxygen gas combining together to form nitrogen monoxide. But this requires heat. You have to add heat to the nitrogen and oxygen in order to convert them into products. So heat goes into this reaction as if it were another reactant. And so we can think of it using the same way that we thought of Le Chatelier's principle before. If we increase the temperature, this increases the amount of heat in the system or increases the amount of a reactant. The system is going to want to resist that change by using up some of the heat in the conversion of reactants to products. In other words, by shifting from left to right. So in other words, for an endothermic reaction, increasing the temperature adds more heat and drives the reaction forward. Removing heat from the system by decreasing the temperature, on the other hand, would have the opposite effect for an endothermic reaction. In this case, we're removing heat, and the system wants to replace the heat that we've removed. It resists our lowering the temperature by generating more heat by shifting from right to left. This means that lowering the temperature of an endothermic reaction will actually cause products to form back into reactants. It'll shift the reaction back towards reactants. As you might have guessed, the situation is completely reversed for an exothermic reaction. In an exothermic reaction, heat is a product of the forward reaction, meaning heat is produced when the reaction goes from left to right. So if you increase the temperature of an exothermic reaction, you're really increasing the amount of a product. That means that this is going to shift the reaction from right to left, shifting it back towards the reactants. Decreasing the temperature of an exothermic reaction, however, will cause the reaction to shift to the right, because now the system is trying to replace the heat that you've taken away by generating new heat of its own. So decreasing the temperature of an exothermic reaction shifts the reaction towards the products. Until now, all of the stresses to an equilibrium system that we've been talking about have the effect of changing the rate of the forward reaction or the rate of the reverse reaction so as to unbalance them. Another way to change the rate of a reaction is by adding a catalyst. We know that adding a catalyst speeds up a reaction by lowering the activation energy. However, since the activation energy represents some pathway on going from reactants to products, it is also the pathway to go back from products to reactants. And so decreasing the activation energy actually increases the rate of both the forward and the reverse reactions. This means that the system will reach equilibrium more quickly, the time to equilibrium will be shorter, but it won't affect the ratios of the reactants and products that are present. In other words, the addition of a catalyst does not change the equilibrium composition of a system or the value of Kc. So this table summarizes some of the effects of these stresses on a system at equilibrium. Again, the addition of a catalyst will increase both rates equally, and therefore it'll have no observable effect on a system that is already at equilibrium. If the system isn't yet at equilibrium, it'll get it to reach equilibrium more quickly, but if it's already at equilibrium, there'll be no change. For changes in the volume and temperature, however, it's more complicated. For the temperature, you have to ask whether it's an endothermic or an exothermic reaction, and then think about whether heat is a reactant or a product based on that. Whereas for changing the volume of a gas phase reaction, you have to consider which side has more moles of gas and which has fewer. So let's take this example of an equilibrium between nitrogen dioxide, nitrogen monoxide, and oxygen, and think about how each of these changes, A through E, will affect the equilibrium. So imagine your system is at equilibrium already. What will happen if you add more NO, nitrogen monoxide? Well, nitrogen monoxide is here. It's a product in this reaction. And so Le Chatelier's principle says that if we add more product, the system is going to want to try to decrease the amount of product. The system decreases the amount of product by shifting to the left, towards the reactant side. So what happens if we decrease the temperature of this system? Well, in this particular reaction, heat is a reactant. Heat is on the left-hand side of the equation. That makes this endothermic. So we can refer back to that chart if we have it memorized, but we can also just think that if we decrease the temperature of a reaction, that's going to decrease the amount of heat available. And so by decreasing the amount of a reactant, the system is going to want to try and replace what we took away. And so to add more heat to replace what we took away, this system is going to, again, shift to the left, towards reactants. So what will happen if we remove some oxygen from this reaction system at equilibrium? Here, oxygen is on the right-hand side. Oxygen is a product. But we're not adding more product as we were with A, we're removing some of the product. So we're decreasing the amount of oxygen. The system is going to want to increase the amount of oxygen in response. The Chatelier's principle says that the system will try and resist the change. If the change is decreasing oxygen, the system is going to want to try to create more oxygen. In this particular reaction, going from left to right increases the amount of oxygen. So this will shift towards the products. What happens if we increase the volume of this reaction mixture? Well, here we can ignore the heat, but we have 2 moles of gas on the left-hand side, then 2 moles of NO plus 1 mole of O2 for a total of 3 moles of gas on the right-hand side. So increasing the volume, remember, is going to add a bunch of new space. It's going to allow the molecules to spread apart. It's going to decrease their concentration. And so the system, in obeying Le Chatelier's principle, is going to try and fill that new space in by creating more molecules. It's going to try and resist the decrease in concentration by increasing the amount of molecules. So the way that this reaction increases the amount of molecules is by shifting towards the side that has more molecules. In other words, shifting to the right. There's more molecules of gas on the product side than there is on the reactant side. And then finally, what happens if we were to remove some nitrogen dioxide from this reaction? Now we can forget about moles of gas, we can forget about heat, and we're just thinking about the material components again. In this case, NO2, nitrogen dioxide, is here on the left-hand side. It's a reactant. And so if we remove some reactant, the system will try and replace the reactant. It replaces the reactant by shifting to the left, towards the reactant side. Many natural biological systems depend on equilibrium reactions in order to operate. So for example, an understanding of equilibrium can help you to understand how mountain climbers can sometimes experience a condition called hypoxia when they get to certain high altitudes. Oxygen is transported in your blood with a protein called hemoglobin. So you can represent the binding of oxygen to hemoglobin through an equilibrium reaction, where hemoglobin plus oxygen produces oxyhemoglobin, and this is a reversible reaction. So wherever there's a high concentration of oxygen, in other words, wherever there's a high amount of one of the reactants, then the reaction equilibrium shifts to the right, and you end up with a lot of oxygenated or oxyhemoglobin. In other words, the oxygen is bound to the hemoglobin. When this hemoglobin transports to another area of your body through circulation where the oxygen content is low, like in the tissues, because the tissues have been using up oxygen to perform cellular respiration, then this reaction shifts into reverse. You have a decrease in the amount of oxygen, and so the equilibrium shifts towards the left. In other words, the molecules of oxyhemoglobin that have reached this region of low oxygen concentration dump off their oxygen that they're bound to and release it into the blood. This provides oxygen for the tissues to use. Now at high altitudes, there's a lower partial pressure of oxygen in the atmosphere, and this causes less oxygen to dissolve into your blood, which is flowing through your body. This is actually a consequence of Henry's law, which we learned back in the chapter on solutions. In fact, Henry's law is also a manifestation of equilibrium between dissolved and undissolved oxygen. But anyway, now that there's less oxygen dissolved into your blood, Le Chatelier's principle says that the hemoglobin-oxyhemoglobin equilibrium is also going to be disturbed. And now, because there's very little oxygen, most of the oxyhemoglobin is going to dissociate. It's going to give off its oxygen and turn back into regular hemoglobin. This is going to deplete the concentration of oxyhemoglobin, which will obviously interfere with oxygen transport throughout your body. So this is a summary of the key ideas and concepts in this relatively short chapter on reaction rates and chemical equilibrium. You should certainly know all of the factors that affect the rates of a reaction. You should know Le Chatelier's principle and how stresses on a system in equilibrium can cause an equilibrium reaction to shift in one direction or another. And you should also have some understanding of equilibrium constants. In this class, we're not going to ask too many quantitative questions regarding equilibrium constants, but it is an important topic, especially because it relates to the way that many acids and bases behave in the next chapter. So the more you can understand the equilibrium constant and the equilibrium expression, the easier some parts of the next chapter will be.